So in the previous video, we actually discussed that the trapezoidal input frequency system digital input, the trapezoidal digital input will harvest an outcome of 0.88 magnitude compared to your analog is 0.9. As you can see, the frequency with the same frequency, alright, this is in the analog system, and in the digital system, the values starts to go a little bit different. Alright, 0.88. That one is 0.9. Alright, if you were to look at the Excel over here, for example, this is initially our frequency, right? This particular frequency is whatever frequency we input, can be digital, or because just take a look with the same frequency, either is it analog or is it digital, they are just purely frequency. But because of putting in the same frequency, we have different outcome in the analog domain and in the digital domain. As you can see, in the analog domain we have 0.99, in the digital one we have 0.88 something. Okay, so let's take a look. If it's a small angle, a small frequency, what do I have? If you have a very small frequency, you see the analog and the digital system are the same. If I were to increase furthermore 0.1, you see there is slightly a difference already, you see. Alright, the values start to go a bit different. If I go to 0.5, they are slightly to go, the digital is slightly lower than your analog. If I go to 0.8, you see digital power has started to decrease compared to analog. Alright, so if the further frequency I increase, you see, if I go to this, you see my digital actually decreases, my power actually decreases with higher frequency. Alright, it's good that our frequency is higher. Alright, it is, how do I say, it is good that if frequency is high, then it is getting lower and lower. Because what do we mean is that because we are looking at a low pass filter, right? A low pass filter is that the higher frequency you are, alright, the higher frequency you are towards the side, your magnitude is going to decrease and decrease furthermore. Right, this is what we have discussed earlier. Right, but because in the digital domain it is decreasing faster than the analog, you see this is 0.48, the analog is 0.69. If I further increase to the cutoff frequency, you see I have half power already. Alright, and you see my digital one is directly going to be 0. You see such of a big distortion between the analog and the digital. If I were to further increase to 5, alright, you see something is wrong already. Your digital actually sprung down. Alright, 7, by right your analog should be 0.155, your digital actually sprung out to increase. You see, if I were to go to 10, your analog actually because if higher the frequency, right, then you have a lower signal. So analog is actually good because you're already above your cutoff frequency, so you shouldn't have any signal at all. So for the digital, there is still certain signal. If I were to go on and on, 12, you see digital actually increases unknowingly. Alright, the digital, because it's governed by tangent, you see. So the tangent actually causes a certain issues with your system. Alright, so therefore with certain frequency you have a certain outcome which may actually distort your signals to a certain extent. Alright, so from here you can clearly see the problem already, right? So in there is just some form of a mathematical representation. In terms of a derivation representation, let us just derive this thing. Okay, so I'll just take in this thing because alright, so I have this thing first. Okay, so if this thing over here is equals to your A, alright, then this means what? Then this means that you have a half power, right? So if if this whole thing is A, so A over A is equals to 1, right? So 1 square divided by 1 square plus 1 square is equals to half. Alright, half power zone. So in such a case that happens, we will have half power. Okay, so therefore we are actually looking forward to that also. We are looking forward to seeing how does this correspond to our understanding of the distortion that occurs. Is that, for example, I'll just switch this side, so I've multiplied t over here, So and then divided by 2, so I'll just switch in sides only. So what I have is 80 over 2. Okay, so as you can see, maybe I can remove the j already, because the j is just indicating that it's an imaginary axis, that's all. Alright, so as you can see, what is the problem over here is that for tangent omega t over 2 is equals to at over 2, then you have a half power issue, okay, or you have a 3 dB lah, minus 3 dB. But it is still considering stable, right? Because why? If you are lower than if you are equals to your frequency, for example, your cutoff frequency is 3, for example. If you are equals to your cutoff frequency, alright, your analog is 0.5, your digital is okay, no values at all. Actually, it's pretty good, because for low pass filter, you want it to be exactly at a cutoff frequency. It becomes 0, right? Because if you remember your cutoff frequency, ideally, alright, you want it to be over here. This is your cutoff frequency, right? Over here your power should be like that, zoom, 0. Alright, so therefore at this cutoff frequency in the digital domain, as you can see, is very good. It's very good. However, nonetheless, there is also a problem. If you have higher frequency coming in, you see your digital magnitude becomes larger already. Okay, so this is the problem that causes the distortion due to our tangent. Okay, so for example, if my omega, alright, is a small value, for example 0.005, okay, so for omega to be 0.005, if a is equals to 0.005, what can we see? Alright, and then t is equals to 1, for period is equals to 1. Okay, if I were to sub in all this value, if omega is equals to a, right, this is when we have discussed for the analog signal, we say that if omega equals to a, we will have half power. Alright, so same thing over there. If omega is equals to a also, okay, which is clearly seen over here, we should also have half power, right? So let's just see what can we get. Okay, so if I were to sub in as 0.005, you see, I would have 0.0025. Okay, if I were to sub in as 0.005 and the period is equals to 1, and it's divided by 2, then I also have 0.0025. Okay, so for very small frequency, when omega is equals to your cutoff frequency, you have half power, because over here they are the same. Alright, this means that over here, this thing is equals to a. This whole thing is equals to a. And we wonder why is it equals to a, because this equation, alright, comes from this thing. So if this thing is equals to a, then the whole thing becomes half power, right? Which is we have shown you over here, right? So in order so therefore we rearrange this thing, alright, so that we can formulate this equation and compare the omega and a, and then we rearrange stuff. Eventually, when they are equals to each other, alright, this means that this thing is equals to a ma, okay. Nonetheless, you can sub in your omega and your a over here. You will see the same result. Okay, you will see the same result. Okay, you can just try to sub in. You'll get back 0.0025 is equal to 0.0025 also. Okay, you can just try it in your calculator in the radian mode. Alright, so if you have a high frequency, in this case if it's 5, if a is equals to 5, then it's really different already. Alright, you wouldn't have the half power already. This can be clearly seen, because if you still remember, your a is your cutoff frequency, alright, your w omega is your input frequency. So if I have to sub in into my this thing over here, you see, sorry, my digital actually becomes way smaller. Okay, so therefore this is the thing. I think you get what I mean already. So the tangent portion is good to a certain extent, but it's bad if your frequency is way too high. You actually lose the issue, how do I say, the purpose of the low pass filter purpose. Alright, because you see the higher frequency I have, if I want to go 100, you see, my analog signal actually becomes way too small already, 0.000. There's no more power, but my digital signal is still spiking because of the tangent. Tangent is always because if you still remember, tangent in the radial mode is going around the circle. It's something like, okay, I think this is a good graph. This is a tangent graph actually. So when you have a low frequency, actually this should cut at the middle point lah. Okay, so you have a low frequency, or you are somewhere over this region. Yes, you have somewhat, the magnitude is somewhat very small. However, if you are reaching pi, alright, because in the radial mode it's just a circle only, alright, and then you may reach pi, 2 pi, things like that. So in the sine graph is something like this, right? So it will still go on in the loop like this. So for tangent it's the same thing. You'll go on in the loop all the way. Okay, so at each of the loop, when it is at pi, you will spike up. Okay, so therefore this is the dangerous part. When it spike up, you'll cause a trouble. So you'll lose the low pass filter system. Right, or lose the purpose of the low pass filter already, because you want to, low pass filter is to filter out the high frequency. But however, if you have a high frequency that corresponds to pi and minus pi, alright, then you would actually spike your digital output to be high, which will cause distortion. Alright, so therefore this isn't much of the case. Coming back here to the S domain and Z domain, we say that for the trapezoidal, or we can say that the trapezoidal can be called bilinear or twisting, whatever you want to call him. Alright, this thing over here, this thing all over here, if you were to plot all the left half plane, you actually plot it inside the Z domain within this circle. We say that it is stable. Although this is stable, you may actually have signal distortion. You have a problem with the distortion. You can be stable over here, but you will distort your signal for some reason due to the tangent. Alright, this tangent that causes certain problems within. Alright, so therefore this is something that you need to take note of. And in order to tackle this tangent issue, if you want to have high frequency, alright, such that it will not cause distortion or things like that, if you want to remove the, if you have, for example, your purpose is to have a low pass filter. Okay, your purpose is to have a low pass filter. If you have a high frequency all over here, you predict that there will be a high frequency, alright, because at this high frequency in the digital domain, it may actually spike up. Alright, so therefore you'll have something like this. Sorry, maybe something like this. And over here you'll spike up, and then it continues to spike up, and then later on you'll go down again. So over here, there will be a distortion over here clearly, right? Because by right low pass filter all the way, it should be all the way down. But because of the tangent stuff, it actually spike up and things like that going on. Alright, so the purpose of this, to prevent this thing from happening, we will want to use the pre-warping. Alright, so there will be a method of pre-warping for a certain special frequency that you may predict that the particular high frequency will cause problem in your low pass filter. Then you will definitely need a pre-warp to pre-warp the particular frequency such that it will not cause you any problem at all. Alright, I think I think only because like say until like macam only but later wrong. Okay, but just take note lah. So therefore in the next video we will discuss with you how to apply the pre-warp. Okay, how to apply the pre-warping. We're using a exam question. Alright, so yeah, so I think you understand the distortion. So we will now use the pre-warp to actually illustrate the meaning of how to pre-warp to get something out. Alright, so in the next video we will not talk about low pass filter anymore. So low pass filter, we will not talk about it anymore. We'll talk about something else already. Okay, so I shall see you in the next video to illustrate how to pre-warp your particular frequency. Okay, see you there.